kind of a random question. So I'm going to be missing class in a couple of weeks, so I was wondering if you're putting these on continuously?
Yeah, they're going up within 48 hours, right?
I don't know, yeah, I talked to them. We said at least by the end of week or so.
Yeah, by the end of every week. Yep, okay. Oh, I ought to give you a schedule for... And we had a problem with the second videotape this semester. So what we did is we just inserted the second class from last semester. But there's no, it's got to be somewhat close, but there's no, since I don't really work from an exact outline, I never know what I'm going to say until I get to class, okay? Not that I didn't think about what I might say, but I never know until I kind of get in the flow of it. So it's no big deal. You're not being quizzed. So who cares, right? I mean, if you missed a class, you would have missed a class and you wouldn't have even had a videotape to watch, right? So essentially we all missed class that day, except for the ones that were here. Okay, so anyway, but anybody watches it on video some other time, we'll get a slightly different version. Which is why it's better to come to class so I have someone to talk to. I can't lecture to an empty room. This is sort of, you know, I get the adrenaline going and you know, start getting into it. Huh?
Isn't that what Isaac Newton did?
I don't know.
I think he lectured to like empty classrooms.
Did he? Oh, okay, well, maybe that's why I couldn't understand it when I was a freshman. So anyway, he was...
Yeah, no one was interested in what he had to say.
Well, I've been in that situation. Go to some professional society, nobody wants to hear this kind of detailed stuff that everybody does research on. Took me a few years to figure that one out. First I realized there was only two people in the room who knew what I was talking about. It's typically myself and someone else might be interested in it. And then after, well, about 1988 I took this senior executives program over at the Sloan School, and Lester Thoreau was lecturing, and he used to get, this 1988, he used to get $30,000 a lecture. Not at MIT, but if he went and talked to some board of directors or some conference or something, he would charge $30,000. He was a very engaging speaker, and so the first time I ever heard him, I was there with 49 other people from the senior executives program. These are fairly senior people in industry. I was the only academic in the room. But we were all just enthralled with what he had to say. The second time he only came twice in the 9 weeks. And everyone else was just enthralled again, but I was sitting there analyzing. I was the engineer. I was analyzing, why is everybody so interested in what he says? And it wasn't, at the end I realized it wasn't anything that he said that I didn't already know, but it's the way he said it, okay? For example, are we on the tape? It's okay, yeah, okay. Anyway, just for example, it turns out, I later got to know Lester Thoreau. He was the dean of the Sloan School of Management later. Actually, he'd just become the dean in 1988. And I remember him giving a talk over at the Marriott Hotel over here to a bunch of people, and he never used PowerPoint, okay? He had a little 3x5 card, and he just kind of, if you saw it, it's kind of scrawled a few words on it, and that was his notes for his whole talk. And he'd get $30,000 and stuff, but anyway, it was the way he said things. For example, he was lamenting the fact that this business school up the river would tend to hire away some of the top faculty from the Sloan School because they had all this money. And he said, but fortunately they tend to hire our extinct volcanoes, okay? And that metaphor of extinct volcanoes does not require any explanation, okay? You know exactly what he means. And I knew he was talking about Robert Merton, who is the father of derivatives along with Black and Scholes. I think Merton was the graduate student. But Black and Scholes passed away. But a few years later, in the I think it's 1990s, maybe it's early 2000s, Merton won the Nobel Prize for derivatives. And of course, in 2008, the whole world economy fell apart because of derivatives. Okay, so not because the theory was wrong, but because people were abusing it. Hard to believe that someone would abuse something and it had to deal with money, right? Anyway, I could give you another economics lesson on derivatives, but it's not worth it. Anybody have any questions? It's now time to start the lecture. Oh, okay. No questions? If you ask questions, I don't have to lecture. Okay, the themes for Friday, which was mostly a recitation, was the cost of structural materials is closely related to the energy content. And that has changed, particularly over the last 20 or 30 years, from where it used to be the cost of labor. I told you to make a pound of steel back 400 years ago, or a ton of steel, was about 6,000 person hours, okay? Well, obviously, most of that was labor content. Back in 1797, 220 years ago, 97% of the workforce was engaged in what business activity? What was their employment was as what? Farmers. They needed food to eat. And it took 97% of the populace to grow enough food to feed the people. And only 3% of the people were doing all the manufacturing and other things. And that's why productivity and manufacturing growth was slow. And then you had the Industrial Revolution in the 18th century. And then all of a sudden, in the 20th century, we've had tremendous productivity growth, such that when I was working in 1975 for Bethlehem Steel Corporation, half the cost of a ton of steel was labor and half was energy. Today, it's about 95% energy and down to labor cost of 20 minutes per ton. Okay, even if you're paying someone $80 an hour, a steel worker in the United States, and paying them $15 in some other part of the world, which would be a handsome wage in another part of the world, you're only talking about $5 to $30 per ton, and that's only about 10% of the cost, or 5% of the cost of the material, the ton of steel. And energy cost is the dominant thing because productivity has just taken over the last 150 years. And labor is not the major cost driver for materials now. Now, the other thing I showed you was when we talk about structural materials, there's only 6 elements in the periodic table to break the billion pound per year margin. No, it's not 10. This should be 10 to the 12th. That's 10 to the 9th tons per year, right? We can forget the factor of 2 when we're talking orders of magnitude. So 10 billion tons per year. The only 6 things are carbon, aluminum, silicon, magnesium, calcium, and iron, okay, that are used in those quantities. And it turns out we talked about availability in the Earth's crust, and today I put this up and highlighted that it just so happens that most of those are in fairly high supply or availability. Silicon's number 2 after oxygen, and oxygen, if we talked in billions of tons, we certainly use a billion tons of oxygen when we use all that stone and other stuff. Aluminum, not as metallic aluminum, but as stone. Iron is the only metal on here that we use in the metallic state. Calcium is stone. Magnesium is limestone and stuff. Carbon, which is actually fairly low availability in the Earth's crust. What's the availability of carbon in the Earth's crust? Coal, okay? That's not really a structural material, but we do use carbon as wood, and probably into this billion tons per year regime. And carbon's low, but it's sort of concentrated on the very top surface, right? In terms of wood. You don't dig for wood, okay? So availability and cost are 2 of the most important things in material selection. However, today, any questions on any of that? I want to go on and talk about, we've already talked about it. This is this little plot I've shown you, given you a handout on the paper that I wrote on material selection. This isn't my plot, it's Jack Westwood's. But in fact, the usage is proportional to the cost of the material in dollars per pound versus tons per year. And there is a correlation with some scatter. I mean, it's order of magnitude or 2 scatter, but around 7 orders of magnitude. And then we talked about the usage of materials. Let's see, I think if I turn that on, maybe it gets rid of some of the glare. Oh well, who cares? But this is the same thing I've talked about before. Over the life of a vehicle, the value of a pound of weight saved is $2 for automobiles, $200 for commercial aircraft, and $20,000 for spacecraft. And so it really depends on what, another thing about material selection, it depends on what industry you're in. And so if you're talking about shipping, okay, or you're talking about nuclear reactors, they're going to be made out of steel, okay, because it's, and I'm going to show you why. If you're talking about aerospace, and this is the V-22 Osprey in the experimental version, but it's a tilt rotor helicopter. This could not have been made without composites. Okay, it's made out of carbon fiber composites for the fuselage, the wings, everything. It's the first aircraft back in the 1990s ever designed with 100% composite structure. Why? Because helicopters are not very efficient. You have to have a lot of energy to lift a little bit of weight, and the only way to make this thing light enough, you couldn't have made it out of aluminum. It would have been too heavy. It never would have flown. It wouldn't have had any payload. As it is, this will take you can drive a Humvee into that. You can carry something like 24 Marines in full regalia with their weapons and stuff. And that's the only way you could have built it. And this is the X-33 space plane. When you're going to $20,000 a pound for material into space, the goal of the space plane, it always cost about $10,000 a pound to get a pound of useful material into space. Okay, so if we're talking payload into space, and we're talking $10,000 a pound, this was in the early 1970s, NASA had a goal to drop that to $1,000 a pound, and so they designed the space shuttle. The goal of the space shuttle was to drop the cost to about $1,000 a pound of payload into orbit. Okay, that's useful material into orbit. So whenever you read about these things, any Course 16 folks in here, I think we have one. Maybe they're not here today. They say, oh, we're going to colonize the moon. Okay. And all the rich people, we can send all the rich people to the moon. Okay. Okay, because only people who can afford $10,000 a pound, it's going to cost $1.8 million to send an average person just to get them there without their clothes, okay, or anything else. So there's a little problem with this. Oh, we're going to colonize Mars. Oh yeah, really, thank you. Okay, that's because you haven't looked at the cost of these things. But the X-33 space plane was going to fly, it was going to hopefully do what the space shuttle never did. The space shuttle never dropped the price from $10,000 a pound to $1,000 a pound because all the operational problems ended up costing more like $40,000 a pound on the space shuttle. It kind of increased the price by a factor of 4. And now you've got these private companies that are taking over from NASA to put things into orbit, or the Soviets, where economics is a whole nother dimension with different rules. But the X-33 space plane was supposed to be the successor to the space shuttle, and it was going to fly on water, H2O. Okay, 2 hydrogen tanks and 1 aluminum tank, or 1 oxygen tank. The oxygen tank is going to be made of aluminum. I've passed around a piece of one of these 2 tanks. It was a $1.3 billion program to build this half-size model, and this really didn't have any payload, cargo space, or anything. This was just to prove they could build it. The whole thing was a interesting structural problem. These struts and thus had to take the thrust. Those were titanium and Inconel and very heavy metals because they had the strength. The outside skin was actually part of the structure. In fact, these tanks were part of the structure. You had to have multifunctional use of the materials in order to make the thing light enough. And it still cost $50 million to build that tank and $50 million to build that tank. They only weighed about 2,000 or 2,400 pounds, which is pretty light, but $50 million, you can figure it out, it's $12,000 a pound as fabricated. And that's one of the problems with composites. Yeah, they work for military aerospace, they work for aerospace, and they actually work for automobiles. What automobiles are road vehicles with 4 wheels are made out of fancy composites?
Tesla.
Well, is Tesla? Okay. Which is a $100,000 vehicle. And they had to do it because it has all these heavy batteries. What did someone else say? Formula One cars. Right. Formula One. Fancy race cars. Indianapolis Racers, which cost about $1 million. Okay. Fancy composites. Ooh, wonderful. Another place of fancy composites is America's Cup yachts. Okay. Not every ship is made out of steel. The America's Cup yachts are made out of fancy composites. They don't care about the cost because these are billionaires trying to rub some other billionaire's nose in it at the country club saying, I beat you in the America's Cup. Okay. And when you get to one of my classes, I can't remember which one, I bring in a part of America's Cup. A guy who's a graduate of mechanical engineering over here runs a company down in Connecticut, makes specialty hardware for fancy yachts. Okay. And he brought me a broken little hydraulic cylinder. They use 7,500 PSI hydraulics on the America's Cup yachts, which, I mean, even on the V-22 Osprey, they went to 3,000 PSI hydraulics systems to run the controls and stuff, which was a big jump from the typical 1,500 or so PSI, because the higher the pressure, the lighter the weight. And they were pushing for lighter weight. If you run a system at higher pressure, it can hopefully be thinner, smaller diameter tubes and lighter weight overall. Well, they go to 7,500 PSI, and if you have a fracture in one of those things, you got hydraulic fluid that could come out and just cut their arm off. Okay, I mean, take a pressure washer. Okay, a high pressure washer, you can slice your finger off with a high pressure washer at 3,000 PSI. Don't do it. Don't run your finger through the high pressure jet. But at 7,500, you could kill one of those people. But in fact, he brought me this thing, and it had failed, it had split, no one got killed. But they were worried about the safety. But he explained to me, for America's Cup yachts, if the thing doesn't fail every now and then, you made it too heavy as a designer. Okay? Sort of a different philosophy. You should be shaving it down and making it thinner and thinner until it fails on a regular basis. So these are fairly expensive yachts in that you usually are expecting parts to fail and you just replace them, because it doesn't have to last very long. There's a few things like that. So America's Cup yacht has to last for a few hundreds of hours before you trash it and go on to the next America's Cup. There's only one other component that I know, well, I'm sure there's other. There's probably things in nuclear weapons that have to last for a fraction of a second before they're no longer useful. But the engine on a cruise missile, okay, only has to last for about 2 hours. And they make it out of carbon composites, and they can keep it from oxidizing away at high temperatures, but it won't last for 10 hours because it will oxidize away in 10 hours. But it only has to operate for two hours because then you're going to blow it up, okay? So yeah, in selection of materials, it depends on the value of the material and what its cost is going to be. So there's a guy, Bob Sprague, who's retired for 15 or 20 years now from General Electric Aircraft Engines. And Bob had a lot of great quotes. Here's one of them. He was head of materials at General Electric Aircraft Engines. Whenever you first hear about the properties of a new material, write it down, because those are the best properties the material will ever possess. So material scientists are always developing some wonderful new material. And Jim Williams, who was a professor at Carnegie Mellon, titanium expert, went on to be dean at Ohio State. Jim replaced Bob Sprague at General Electric, and his corollary, and this is actually his slide, he gave it to me because we were both talking at a conference once, and he heard me quote Bob Sprague, and he wanted me to start quoting his corollary. Whenever you hear the price of a new material, write it down, because it'll be the lowest price you will ever hear. So people, when they develop new materials, are always touting wonderful properties, wonderful cost, but in fact, over time, you find it's not so great. Now, one of the things that I've looked at over the years is what is the fraction, what's the material cost as a fraction of the whole product cost? If I want to look at this pointer here, okay, I paid $200 for a blue pointer, okay? I think, no, it's maybe 120. But anyway, and I don't know what it weighs, a few ounces, but we're talking $500 a pound. This is sort of well beyond automobiles into the aerospace regime of product cost. But it's a functional material, okay? It's got a little laser. I mean, I don't think the holder is all that valuable, but in any case, for an automobile or an aircraft, typical material cost is about 10% of the overall product cost. And I gave you this paper on materials for 21st century defense needs, where I quoted this. Obviously, in functional materials like semiconductors or spacecraft, it's maybe only 1%. Materials cost are nothing compared to the overall $20,000 a pound to get something into space. However, pipelines, and I just wrote this in the other day because I just learned in the past month, you know, the big transmission towers for the 345 kilovolt, you know, electricity lines, and you see these things? They sell for about $1.30 a pound out of steel, galvanized steel, and that's about 30%. Pipelines and transmission towers, the material cost, the steel is about 30% of the cost. And actually, you know, sinking the poles into the ground and stuff and all transporting them and everything else is only another 70%. Pipelines, the actual material cost, most of it's transporting the pipe, welding it, burying it in the ground, you know, coating it for corrosion resistance before you bury it. Anyway, so pipelines and transmission towers have probably the highest material cost as a fraction of the total installed cost. Automobiles and aircraft are only about 10%. So you buy a car for $25,000, it's got about $2,500 worth of material in it. Actually, it probably has a little bit less. In terms of the amount of steel or aluminum or plastic or whatever that they built that thing out of, okay? Because the value of a pound saved is in an automobile is only about $2 a pound. So if I go, and this is out of Ashby's first edition of his book, and I think I've mentioned Ashby before, but if I haven't, you know, if I'd figured out earlier, I probably would have made this a textbook for the course. This is Michael Ashby's third edition of Engineering Materials, and we'll go through it a little bit more. But if I start looking at the cost of materials, diamonds at about $1 billion a ton in 1980, boron epoxy composites at $330,000 a ton, cobalt alloys, these things are getting almost too pricey even to make spacecraft out of. Titanium alloys, yeah, you can make spacecraft out of that. Nickel alloys, stainless steels. If we get down here at, these are the materials that you can build airplanes out of at $200 a ton, okay, as the product cost. And what can you make automobiles out of? Well, you can make them out of, well, you can't quite make them out of plastic, but silicon carbide, plywood, low alloy steel, mild steel, cast iron, concrete, coal, or cement. So we're sort of limited, okay? You could put aluminum in here, but aluminum is actually up here. Aluminum, yeah, you can make a very expensive vehicle, but if I want to make a $20,000 or $25,000 Ford Taurus or something, you don't make it out of aluminum, okay? Well, this aluminum sheet is $2,200. If it's only 10% of the value, you got to take these numbers and divide by 10. Okay, for the material cost that you're going to pay for it. Because the other 90% is going to be fabrication, inspection, G&A. You know what G&A is? It's called general and administrative. That's all the overhead. Okay? They usually on the budgets call it, the accountants call it G&A for general and administrative. Got to pay the boss something. Okay? This is out of Ashby in his second edition. And here's the relative price. If mild steel is at a relative price of $100 or whatever, for whatever, cast iron is cheaper, ingot iron, softwoods, concrete, fuel oil, cement, and coal. I mean, when you start looking at these things, you realize that automobiles, ships, pressure vessels like nuclear reactors, big heavy structural materials, a limited number of materials that you can use. However, that's kind of an 80,000 foot view. looking at what costs $20 a pound, or $20 a pound saved, or $200 a pound saved, or whatever, over the life of the vehicle. It also depends where the material goes. And so here's a slide that I put together years ago that says if a product moves, like a lot of things that we want, low density is an advantage. For equal volumes, one will pay for the less dense material. And here's actually a curve, calculated it in my head, okay? But if the density is 7, which is steel, which is one of the Achilles heels of steel, is it's a heavy material. You're only willing to pay less than $20 a pound for that material in some application. If it's aluminum, you could be willing to pay 2.5 times as much, okay, on a density basis. Okay, we actually have something called specific, well, I'll get to it later. We often talk about specific properties, which is the property divided by the density. Okay, so what are the examples of paying more? Okay, if something moves, anybody know what the sprung weight is on a car? They call it the sprung weight in the business. It's everything that's on the axle, like the wheels, the brakes, the axle itself, and it's got springs that connect it to the car, to the rest of the vehicle. And why do you have the springs? Because those roads are bumpy. Okay, you want a nice smooth ride for the passengers. The passengers, the body, the seats, that's all unsprung weight. Okay, it's not using springs to smooth it. Sorry, the springs have already been used to smooth out the ride. But you hit a pothole, a lot of those in the Boston area on the roads, and that's the sprung weight. And so the wheels move faster because they're going around in circles. And they have to go around in a circle for the car to go straight, so the actual outer rims of the wheels move faster than the vehicle. Actually, do they move faster than the vehicle? They move at the rate of the vehicle. But the other part inside, smaller radius, moves less fast. In any case, the brakes are on the wheels, and if you could make the brake calipers lighter, then you would be able to save weight on the axles and the springs and everything else, okay? Because the sprung weight is moving and is taking more harsh environment than the unsprung weight, and therefore you can save weight in other parts of the system, the overall design. A better example that I like to use is turbine disc in aircraft. Okay, the Air Force has spent billions of dollars trying to make Blisk, okay, a bladed disc. So you know what a turbine engine looks like, and you know what the disc, and it has turbine blades sticking off around it. So this sort of looks like a sun from elementary school, paint it yellow. In any case, they attach the blades, which are this fancy material that can't be welded generally, with this, they call it a Christmas tree structure, okay? This flange and all this weight down here, this is actually probably half the weight or more of the blade. If I could weld the blade directly to the disc, I could get rid of this big heavy flange on the end of the disc. And these discs, depending on the engine, could be traveling at 18,000 RPM, okay? Or maybe only 2,000 or 3,000 depending on the size of the engine. But if you can get rid of this big heavy rim, then you can lighten this whole thing, and the Air Force estimates you can get 20 pounds out of a single disc, and there might be 3 or 4 discs in the engine. There might be 2 engines, might be 4 engines on an aircraft. So you could probably save a couple of 100 pounds off the engine or the engines in a military aircraft. And I didn't tell you, but I keep on saying commercial aircraft is $200 a pound. I didn't tell you, but studies of military aircraft show that $1,000 a pound is the bogey for a military aircraft. You can either carry more fuel to get more distance, or you can carry more payload to kill more people, okay, on a military aircraft. And it's worth about $1,000 a pound over the life of the vehicle. Well, if I can take 20 pounds off a disc, I can take 200 pounds off the engines. It means I can take 2,000 pounds off the wings and the rest of the structure, which have to hold those engines. Okay? So this collateral weight savings, if I'm taking it off the highest speed part of the aircraft that's moving the fastest, I can get all kinds of follow-on savings. That's true in automobiles, it's true in most moving vehicle structures. You have to see how fast is the part that's moving in whatever you're trying to design, and you'd be willing to pay significantly more, up to 10 times more, for something that has to move very fast to save weight. So 25 years ago, they tried to use aluminum calipers for the brakes on cars. You know, you got disc brakes, okay? They don't try to use aluminum for the disc in the disc brake. That's made out of cast iron for some reasons have to do with wear resistance and frictional properties of cast iron and whatnot. But they wanted to just, the brake pads, which are held by this housing, the housing was made out of ductile iron, and if they could make that out of aluminum, they could probably take 15 or 20 pounds off of weight, the sprung weight of the vehicle, which is worth more than $2 a pound. It might be worth $10 or $20 a pound. Well, they tried to do it, and the problem was brakes heat up if you use them really hard. And some of these aluminum alloys aren't much good above 200 degrees Fahrenheit. They start to creep. And if your brakes start to creep, they call that fade. And that means if you slam your brakes on hard 2 or 3 times, or you're coming down from Berthoud Pass on Interstate 80 and heading into from Salt Lake into Denver, closer to Denver. Anybody know that area, Colorado? Big long downward slope. Got lots of turnoffs for the trucks because they go rolling off the mountain. Probably lose 20 trucks a year just going over the edge, right? The guy just opens the door and jumps out and lets his car go, okay, down the mountain. And they have these ramps where they can slow down, but you have this long thing. It's Eisenhower Tunnel. Okay, Eisenhower. You're coming into the Eisenhower Tunnel, you got like 20 miles of just coming down the Rocky Mountains at about 6% grade. Well, if your brakes fade then, it means that they no longer are braking. Okay, not a good thing. So it turns out aluminum brakes didn't work, although they've developed new. It took them 25 years. I've read in some of the newer cars they have aluminum brake housings. Okay, so they have, because of the creep problem, they had to overcome that creep problem. But it took them a couple of decades to figure out what the right alloy would be. Okay, so far as that would go. The Air Force would love to make Blisk, and they've had big programs to do it. The only aircraft that I know that actually has a cast integral disc and blade, and I'd like to get one, is an M250 Detroit Diesel Allison, which is now Rolls-Royce. And they make like 10,000 or 20,000 of these engines. They go in helicopters and small business jets and things like that. Very high volume engine, but it's a cast technology. Everything is cast. It's not as fancy as these single crystal blades. It's not as fancy a design. It's a 30-year-old engine. But they do use Blisk technology as far as that goes. Okay, so that's another important point. The faster something goes, the more you're going to pay to use it. Okay? We don't care about nuclear reactors. Hopefully they don't go very, very fast at all. And when they do go fast, we don't want to be around them. Okay? Ships don't go very fast, except now the Navy is interested in higher speed ships for the littoral battlefield. Okay, the littoral battlefield is anything within about 100 miles of the coast, and so because of terrorism and stuff, they don't need the same number of great big aircraft carriers and nuclear submarines that are pretty slow and ponderous. They want some ship that can go at 60 miles an hour and go catch those pirates off Somalia or whatever. Okay, so they have to go to aluminum ships. And there's all kinds of problems, even though we know how to use aluminum in a lot of applications, and we've been using them for ships. When you start putting them in these bigger ships, you start running into problems. the Swedes about 20 years ago scooped the rest of the world by building a all-composite frigate called the Visby. Okay, anybody ever heard of the Visby? So this was an all-composite corvette. Okay, you know what a corvette? It's smaller than a frigate. You know, we make frigates out of a destroyer. If you're a destroyer is sort of a big ship, but now we got such high technology weapons. A destroyer probably has the firepower of an old battleship or more nowadays. So we don't build battleships. They're expensive, they're big, they're just a perfect target. So we started building destroyers 25 years ago. Today we build mostly frigates, because frigates are small, like small destroyers, half the size of a destroyer. Well, a corvette's even smaller. The Israeli Navy uses lots of corvettes, okay? It's bigger than a PT boat from World War II, but it's not a very big ship. So the Swedes built the Visby out of all composites. They wanted to prove they had the technology to build the world's best ship. And all the other countries thought, oh, they scooped us. Yeah, well, they scooped them until they found out that the modulus of all those plastics, the stiffness, was such that the sea-keeping ability, which is when you go out there in those rough North Sea conditions, the Visby just would flex. And so the Visby had about a lifetime of about 3 years before it had so many cracks, okay? It's fine as long as it stays in port. What as Admiral Grace Hopper said, a ship is safe when it stays in port, but that's not what ships are for. Anybody know who Grace Hopper was? She was an admiral. I think she may have been the first woman admiral. She invented COBOL, which was a business language, computer language in the 1960s. She rose to be an admiral, and she was sort of kept around until she was about 85 or 90, because she was just a very, very accomplished person, and Congress had to pass some laws so the Navy couldn't force her to retire and stuff. But anyway, but she said, you know, a ship in harbor is safe, but that's not what ships are for. So they built the Visby out of composites. It was sort of a disaster. So people would like to make lightweight things, but there are certain material properties that are critical to a number of designs. And when you select materials, you've got to think about some of those things, which not everybody does. Okay, any questions on any of that? Yeah.
What was the problem with aluminum?
There wouldn't be a problem with aluminum. It's just the lighter you can be, the faster you can go in that ship. That Visby, when it was going all out on a nice smooth lake or on a smooth ocean, could go probably 20–30% faster than an all aluminum ship of similar size. Okay.
You said that there's difficulty with transitioning, with actually using aluminum for the large boats.
Oh, well, the problem with the larger boats with making aluminum is cracking, fabrication, fatigue, cracking. They don't have the experience. I mean, it's not really a problem they didn't have when they first started building steel ships, but there's a learning curve of how to do the design. The way you design for aluminum is not the same way you design for steel in terms of welded construction and fatigue cracking and things like that. So yeah, okay, thank you. That was, I didn't explain that. Whenever you go to use a new material, there's always a learning curve. When Audi went to build all aluminum automobiles, even though they had been built by, you know, for J.P. Morgan back in the 1930s, he could afford to have his cars repaired. But when they went to high volume production, they started running into lots of problems that they never realized they would have. But then you work your way around and you learn to design around those things. Okay, yep.
How do you feel about the USS Zumwalt?
Zumwalt is the
Aluminum composite destroyer, the new.
Well, I don't really know that much about it. I mean, have they built one? They were going to build one, but it's going to be a $2 billion ship, right? $3.5 billion. Yeah. Okay. So they're not going to build very many. This is one of the problems when, in the military, just in general, they want to have all the bells and whistles. Okay. It's sort of like the town I live in. Once they have the oldest public swimming pool in the nation. Okay. It's the Underwood Pool. And Underwood was a professor at MIT. He lived in Belmont, and he had a nice little estate right near the center of town back in the 1990s. Underwood doubled, actually he wasn't an MIT professor. He was with Prescott, and he and Prescott perfected canning. You ever had Underwood deviled ham? It's like pure fat, okay? But anyway, Underwood deviled ham was down in Dedham or whatever. He lived in Belmont, and when he died, he gave his property to the town. And so we have a 100-year-old swimming pool. They decided it's not good enough. And of course, all my neighbors, oh, we're going to get a new swimming pool. It has to have this and it has to have that. Well, this is just like the Admirals. You know, the Zumwalt has to have this and it has to have that, and you end up with a technology package that no one can afford. We're going to end up with a pool that no one can afford, except they will just tax me. Okay. So that's my feeling on some of these things. The Zumwalt is designed to wipe out major capital ships of other nations. Now, what other nations have major capital ships that we need to wipe out? You ever thought about that? The U.S. Navy has more capital ships than all the other navies in the world combined. We have more than 50% of all the capital ships in the world. Who else has aircraft carriers? Well, the French have 2 or 3 aircraft carriers. The Russians just bought an aircraft carrier from the French. Okay? Who else has one? Anyway, very few people have these $15 billion aircraft carriers. An aircraft carrier is not a warship. It's basically an instrument of intimidation in peacetime. Okay? You go set an aircraft carrier off someone's coast, and you just have enough to destroy their nation, and they know it. Okay? So you can intimidate people by, and if you send 2 carriers, that means you're really serious. Anyway, you can also send it. Remember they had the tsunami in Indonesia? And there's actually, if I can find it, there's a great quote about some Frenchman complaining about those stupid Americans, and you know there was this tsunami and people were starving and stuff, and what did the Americans do? They sent an aircraft carrier. And he was at some cocktail party at some State Department function or something, and he was just mocking the Americans. So, what are they going to do to help these people? And some American diplomat says, well, a modern U.S. aircraft carrier has 2 fully equipped hospitals. It has like 24 helicopters. It can generate enough fresh water out of seawater for 20,000 people a day. There's 5,000 people on the ship, but they have a little excess capacity when they're not running full steam. You know, by desalination plants. And he goes on and on about all the things that an aircraft carrier can do. And if you park it off the coast of some places that have been decimated, you can bring hospitals, water, helicopters as aid. And he says the United States has 15 aircraft carriers. How many does the French have? And the guy kind of crawled in his hole. It's just kind of one of these quotes. So an aircraft carrier is an instrument of diplomacy and intimidation. It's not really, I mean, if we ever start having to use aircraft carriers for a real all-out war against the Soviets or the Chinese, then we got bigger problems, okay? What the Navy needs is a lot of lighter ships. So the Zumwalt's, it's a perfect ship for 1980. It's not the perfect ship for 2010. But Zumwalt was a great admiral, okay? He was, if you know anything about Admiral Zumwalt. Anyway, other questions? So did I answer your question? Did I answer your question? Okay. Okay, so I wanted to switch gears and talk, oh, I do have something about lightweight, okay? So here's an example. You can pass that around since you're the only one. This is aluminum. You can feel the weight. This is magnesium, 40% lighter than aluminum. This is zinc, almost the same density as steel. So you can compare the 3 materials. I didn't have a 1-inch steel, 12-inch long bar. I don't even remember what the density of zinc is. I meant to look it up, but it should be on my periodic table, if I can find my periodic table. Where did my periodic table go? Oh, here it is. So if I look at the periodic table, density of iron is 7.8, density of zinc is 7.2. So steel is heavier than that bar of zinc. Okay, so if you want to feel the difference between steel and aluminum, it's almost the same. I also have this. And we can look at that periodic table and we can talk about different elements. I have this because this is a beryllium copper alloy. Yes?
Is zinc used for anything other than galvanizing?
It's made cheap metal parts that you can die cast zinc parts. It used to be the handles in automobiles were zinc die cast. Now a lot of times they're plastic. But a lot of die cast components, small little parts in the old days. Typewriters was, IBM had a huge business in die casting zinc parts for typewriters and computer printers and things like that. The biggest use of zinc is in protecting steel from corrosion.
I think I've seen it in corkscrew or the cheap ones too. They are cast.
Yeah. Yeah, cheap castings, okay. Basically cheap castings. They're also they make pennies out of zinc. It's got copper on the outside. But zinc, if you look at the real Achilles heel of zinc is its corrosion. Okay, actually it's one benefit. If you use it as an anode, it'll protect almost any other metal except magnesium. Magnesium is the only more electroactive element than zinc, if you look at the galvanic series. So zinc protects anything from corrosion except magnesium. And it's relatively cheap, but it doesn't have great strength. I mean, if you got handles on a car or, corkscrew, I mean, most people don't have enough strength to break a corkscrew housing, right? So far as that goes. Other questions? So if I want to talk about some of these other elements on the periodic table, and we will get to some of these later, but let's take beryllium. If you go look in the Ashby Handbook on price and availability, you'll find beryllium is off the charts, a couple of $100,000 or $100,000 a ton or something. I wanted to get a piece of beryllium, and to buy a 1-inch disc, 15 thousandths thick, they wanted to charge me $1,000. Okay, Mike Tarkanian knows a member of the department who works for Chase Beryllium and Copper, and we were going to try to get a chunk of beryllium. Beryllium is actually about the same density as that magnesium that she's got in her hand. Okay, so it's not that much lighter, but it has higher temperature capability. It's got great low coefficient of thermal expansion, so when you're building a space telescope where you can't have big differences in thermal expansion because you got the sun heating things to 150 degrees centigrade on the day, and at night it's down to -200 centigrade, you don't want to have a lot of thermal expansion. So beryllium's a wonderful material, but my other possibility was I bought a beryllium copper wrench. This only cost $120. I could have bought this wrench out of steel with chromium or zinc plating for all of 20 bucks, but I could buy beryllium copper. Now beryllium is used as an alloying element to harden it, so this is just as hard as a steel wrench. Okay, it will not wear out. Why would someone pay 120 bucks for a steel wrench or for a beryllium copper wrench? Pardon me? Nope, it's not lighter. You can pass it around. It's actually a little bit more dense because copper's heavier. Yes?
It's toxic and you can feel your
Well, if you breathe beryllium, if you get beryllium powder in your lungs, 10% of the population have a genetic predisposition to berylliosis, and you will get berylliosis, and you will soon die because you will grow these big nodules in your lungs, and you will just slowly suffocate to death over several weeks. The first berylliosis case ever discovered was at MIT, right after World War II, right up there where the Baybank, or the little kiosk is in the parking lot, the corner of Mass Ave and Vassar. There was a building there once. And during World War II in the Manhattan Project, they were machining beryllium, which is a nice new material. And several of the people there got berylliosis and died. And so they learned about berylliosis. Okay, so it is a very toxic material in any form, oxide, metallic, but you have to breathe it into your lungs to have the problem.
The actual answer is
Yes, it has high thermal conductivity. It's not just that. They use them in mines. because you cannot draw a spark. If that was steel, I could take two pieces of steel and hit them together to get a spark. And if I'm working down the mine, kaboom, because there's plenty of methane in the air, potentially. I can go and buy a full set of tools at Sears or Home Depot for $400, right? Nice tool set, right? $400. I can buy the same thing if I go to Brilco online, which is where I bought that for 120 bucks. And I could have gotten any tool you could imagine. And they're all proportionate. I could have bought an entire set for $4,500. And someday when I feel like it, I may buy that full set of beryllium copper tools. But that's if you're working in a mine underground or any type of potentially explosive environment. So your capacitor thing, I'm not sure. But they were doing it because they wanted to avoid sparks. Okay? You can bang the tools together and you will not get sparks, because it has high thermal conductivity. I take two pieces of steel and I hit them together, and the friction will raise the temperature to 1,000 degrees. I can send off a little chip of metal and it will be glowing red, and it will ignite flammable gases in the environment. I could bang two pieces of beryllium copper together till the cows come home, as they say, and I will never get a spark, because the high thermal conductivity, the frictional heating is probably not more than a couple hundred degrees. Okay? So if you're a Boy Scout or a Girl Scout, don't take a beryllium copper tool to do your spark starting fires. It won't work. Okay? Okay, other questions? No? Okay, so we've had enough of that. I told you about competition among materials, and I want to start that today. And I showed you the competition among plastic beverage containers, aluminum. They actually have steel, soda cans back 25 years, 30 years ago when I lived in Japan, because the Japanese government, this is an externality, didn't want to support the aluminum industry. They didn't have a domestic aluminum industry. They did have a domestic steel industry, so they had steel cans. But they corrode a lot easier than aluminum. But there are other things. Conveying water over the ages. What was the first material people used to convey water? Okay, they may have had to go down to the stream, and if they had a bucket made out of clay or something, clay pot, or maybe they just scooped it up in their hand, cupped their hand. But after that, if they wanted to convey it, what might they have done? They could have used animal skins. I was actually thinking of soil. They might dig a hole and they make a trough, except it leaks through. So what did they use next? They probably would have lined it with wood, because they had lots of wood. It was easy to work wood. After that, they might use stone and mortar. Yeah, they could carry it in animal skins. That goes with my beverage container. Okay, I should have gone to animal skins for beverage containers. But to convey water, like pipes, is what I was thinking about. First, they probably dug a trench. That sort of leaked or seeped into the ground. Then they used wood. Then they used stone and mortar. Then they used concrete. The Roman aqueducts were concrete, right? Then in the 18th and 19th centuries, they were using lead pipe. My house was built in the 1930s, so it's 85 years old now. When I first moved in, there was one lead pipe left in the house. It was down above the laundry sink in the basement, and I had it taken out. But anyway, but they built the house in the 1930s, and they had lead pipes in part of the house. They didn't always have it for the drinking water, but anyway. By the time I got there in the 1970s, most of it had been replaced with copper pipe. But copper pipe didn't really come into its own until after World War II as a building material. They still use galvanized pipe, zinc-coated pipe in many parts of the Midwest. Okay, if they have the right water chemistry, you can put galvanized pipe in your home, convey water. It's zinc-coated pipe, inside and outside, and it will last for 40 or 50 years. Use in New England with soft water, where you have pH rainwater of 5.5. The water that comes from the utility is probably pH 9. It might last well at pH 9. So they went to copper pipes. But that is not necessarily the best material. Copper and brass, it's actually pretty good, but it's expensive. Okay? So people have gone to, and I'll pass this around later, plastic pipe. This is PEX, polyethylene X, okay, PEX, and the X means cross-linked. Remember Charles Goodyear? You don't remember him. He died before you were born, before I was born. But he cross-linked rubber with sulfur, and so he had these long polymer chains. Polyethylene is long polymer chains. And he found that if you added sulfur compounds to the latex rubber, you could get a hard rubber rather than a soft latex. And vulcanization, yes. So it's called vulcanization. Charles Goodyear. Well, they learned to do this with PEX plastic tubing in an economical way about 30 years ago to cross-link polyethylene. And this stuff is stiffer than most polyethylene you might look at. In fact, I have a piece of polyethylene here I showed you. Okay, this is pretty flexible. This is nowhere near as flexible, okay, even though it is tubular. But in any case, PEX A is electron beam cross-linked. And we can talk about that tomorrow. Why do you use electron beam to cross-link something? And PEX B is chemically cross-linked. They actually put a chemical in to break some of the chemical bonds. And they get cross-linking between the chains and makes a very stiff, rigid plastic that can take 100 psi. This actually says, I don't see it, but most of the PEX is rated for about 200 psi pressure, which is much more than you need for conveying water in a home. So much of the water in homes is now plastic. But all that from galvanized pipe, from lead pipe of 300 years ago to galvanized pipe of 100 years ago to copper pipe of 60 or 70 years ago to plastic pipe of the last 20 years, tremendous change in the materials we used from stone, clay pipe and concrete aqueducts and things like that we used for thousands of years. And I'm going to give you another example of tomorrow of what we've done for gas piping. But just to give you a hint, anybody know with first gas piping in the streets of Boston, what material they used? Wood. Yep, I'll tell you that story tomorrow. Okay, thanks.